Welcome to the Space Telescope Public Lecture Series. Tonight's talk, The Total Solar Eclipse of April 2024, by Michael Kirk of the NASA Goddard Space Flight Center and John Maple of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers from the Office of Public Outreach here at the Space Telescope Science Institute. And as always, I want to thank the tech team that brings this to you, Thomas Marufu and Grant Justice. Our upcoming talks. In April, we have a talk on gamma ray bursts, spectacular explosions from the distant past. And this one is a transatlantic talk from Giovanna Pugliese from the University of Amsterdam. So this will be a lot of fun. In May, we have Stellar Astronomy in Search of Dark Matter from someone at our own institute, Eduardo Vitral. And in June, we will talk about Webb observations of planet formation. Studying the formation of planets is one of the main drivers of the Webb Space Telescope, and Nicole Arulanantham, I really gotta practice these before that comes up. Nicole Arulanantham will be talking about that in June. If you want to find the full schedule, such as it is, you can find it on www.stsci.edu/public-lectures. And you can see in the lower left of that screen, you can see that we have links to our webcasts of previous talks, both on the STSCI webcasting site and on YouTube. In the lower right, you can see a little box where you can enter your email address and subscribe to our monthly postings, which are reminders of what lecture is upcoming and when the lectures, webcasts have been, reposts have been posted. Further on that website are the details of our upcoming and also our past lectures. If we go into one of those, you can see that we have the description of it. We have the links to the STSCI webcast and the links to the YouTube after it has been done. Our email, as I told you, it's easiest to just sign up at the website, but you can also get reminders, sign up for our YouTube channel, which is youtube.com/Hubble Space Telescope. You'll get new video notices and reminders of our live events, such as this one. And finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. If you would like to follow our institute on social media, we run the social media channels for Hubble Space Telescope, for the Webb Space Telescope, and for our institute on Facebook, X, YouTube, and Instagram. The news for the universe from March 2024. I'm only doing one story tonight, but it's a combination story, and it's quite a story. A supermassive black hole at the dawn of time. Now, this story starts with a Hubble discovery back in 2016. And it was in this survey, the Great Observatory's Origin Deep Survey, Northern Field, which henceforth will be known as Goods North. And in the Goods North field, they looked at tens of thousands of galaxies, and they discovered one object in particular that was of particular interest. And it's been called GNZ11. And the GN, of course, stands for Goods North. The Z11, well, that has implications for the distance of the galaxy, the redshift. All right, let me explain that a little bit in detail. So when you look at the spectrum of a galaxy, there is a particular feature in the spectrum called the Lyman break, okay? And short word of the Lyman break, there is very, very little emission, okay? So there's the big jump in the spectrum, in the brightness of the spectrum at the Lyman break. And when you get a highly redshifted galaxy, i.e. the light has been shifted toward the red to longer wavelengths, that Lyman break can pass through out of the ultraviolet across the visible part of the spectrum and into the infrared. That's for a very highly redshifted galaxy. All right. And so when you look at that galaxy, if you could get its spectrum, what you would see is that in the infrared, you're getting a good amount of brightness, but then there's this big drop and almost no brightness shortward of the Lyman break. And that gives you a good measure of the redshift, how much the light of this galaxy has been shifted. So when they looked at this galaxy in Good's North, they did not have a spectrum, but they did have several filter band observations. They had observations in the blue/ultraviolet, and they saw nothing. They had observations in the visible to the near infrared, and they saw nothing. But going as far into the infrared as Hubble goes, they saw something, which tells you that the Lyman break was in between the filters where they saw nothing and when they saw something. And from various scientific ways you can do it, you can estimate the redshift. Okay, and the redshift for this galaxy, as you might have guessed, was estimated to be at 11.1. Now, that may mean nothing to you, okay? But it's actually extremely important because most of the galaxies that we were discussing when I was in graduate school, way back when, right, were redshift 2 and 3, and the really high ones were 4. All right, now we're up at redshift 11. That means that this one is much, much further out in space and much, much further back in time. And as you can see on this slide, this galaxy at redshift 11 would be 13.4 billion light years distant. And in a universe that's only 13.8 billion years old, that means you're seeing this galaxy as it existed 400 million years after the Big Bang. All right, in 400 million years, you're developing this, well, I don't really want to call it a galaxy. I'd rather call it a proto-galaxy, okay? Because it's in development, okay? All right, but if you notice from that previous slide, the observations for this are best done in infrared. And Hubble isn't the best telescope in infrared anymore because we have the Webb Space Telescope. So Hubble did its observations of Good's North. And of course, Webb did its observations, has now done its observations of Good's North. And they don't cover the same field, but they do cover that important region where the galaxy GNZ11 is, okay? And it's actually in the lower right corner in this image, and here it is, okay? So they made sure when they did the Good's North field with Webb that they got this galaxy in the field of view. And let me blow this up for you. All right, you can see the Hubble observation is kind of fuzzy on the left, but the much clearer in the infrared, because Webb is an infrared telescope, it's got a much clearer, much finer observation of this. And from it, they can see that there is a definite core to this galaxy, okay? It's hinted at in the Hubble observation, but you can definitely see there's a core in it. And what's further is that they could tell there were winds around it, okay? And so you're getting this high density material and these winds, all right? And the conclusion from that is that this galaxy, even 400 million years after the Big Bang, already has a supermassive black hole. And they estimate the mass of this black hole to be 2 million solar masses. Now, how big is 2 million solar masses? Well, the Milky Way, the supermassive black hole in the center of our Milky Way galaxy is about 3.6 million solar masses, okay? So in the first 400 million years of the universe, you're building a supermassive black hole that's half the size of ours as it is today, 13.8 billion years into the universe. That's really kind of cool. And then, I don't know if you can see, there's a bit of fuzzy stuff around that central clump here in GNZ11. Well, they're able to take spectra of that. And in the spectra, they were able to find helium, okay? And so you can see this is the spectrum, the brightness on the y-axis and the wavelength on the x-axis. And there's a definite signature of helium. Now, but that's not unusual. We expect to see helium. But what's really unusual is that they did not detect any other heavy elements beyond helium, okay? Now think about this. In the Big Bang, you create hydrogen and helium. And then you have to have stars exploding and stars forming and stars cycling through to get all of the heavy elements. So the first stars that form in the universe are only going to be hydrogen and helium. We call these population 3 stars. These are stars that are collapsing out of the primordial gas that comes to us after the Big Bang. Now, this helium observation and the lack of other heavy elements doesn't prove that what we're seeing here are, pop 3, the first stars, but it's suggestive that we might be able to try and probe those very first stars that form in the universe and what their characteristics are. Because when you form just with hydrogen and helium, it's actually going to be a different type of formation process. The cooling as the gas collapses together is different than when you've got all these heavy elements around. So this is a really cool topic, but we haven't quite gotten there. We have evidence of the most distant supermassive black hole we've ever seen. And we have hints of the formation of primordial stars. That's really cool. All right, let's get to our main talk tonight. And the main talk tonight is by two people. The total solar eclipse is such a big event. We wanted to bring you all sorts of things, both several aspects of it. And our first speaker tonight is Michael Kirk from the Goddard Space Flight Center. He is a research astrophysicist and the leader of the Heliophysics Education Activation Team, otherwise known as NASA HEAT. He got his undergraduate degree in physics and astronomy from Whitman University and I have to say this, Walla Walla, Washington. Let's go Walla Walla. And he got his master's and PhD from New Mexico State. He then went on and became a postdoc at Goddard Space Flight Center. But then he left Goddard Space Flight Center, went on some tour around all sorts of other places, bouncing around. But he ended up back at Goddard Space Flight Center. However, he's not actually at Goddard Space Flight Center. He's in remote work, and he's actually in Portland, Oregon. He joins us from Portland tonight, where he told me that he roasts his own coffee and is a partial investor in a winery, because I don't know if you know, Oregon has some pretty good wineries up there. So take it away, Michael.
All right. Thank you very much. So let's go back one slide here. Thank you. Thanks, Frank. And I'm terribly happy to be here today because I get to be a rock star bringing you back down to Earth. We flew all the way out to the beginnings of the universe, and now we're going to go to something that's very much in front of us, which is a total solar eclipse. I imagine most of you are relatively familiar with what a total solar eclipse is, but I wanted to just give a refresher to those, and I have a couple of animations here that I particularly like. On the left, what you're seeing is an animation of what a total eclipse will look like, where you have the moon passing in front of the sun, completely blocking out the bright disk of the sun. So for just a fleeting moment, you can see the solar corona. So the solar corona is the outer atmosphere of the sun. It's this gossamer, beautiful structure that exists all the time. In fact, you could even argue that the Earth is in the outer solar corona, but we normally can't see it. It's the sun's disk, I think, is about 1 billion times brighter than the solar corona in visible light. So unless we can get rid of that bright disk that's in the way, we'll never be able to see it. In addition, I have a great little animation here that's showing you a little bit of the geometry of it. And the geometry is important because this is really special. This geometry where you get the moon blocking the sun and casting a shadow onto a body is unique. We know of no other place in the universe yet. I'm sure there's other places, but we haven't seen them yet. There's no other place in the solar system. We know of no other place in the universe where this exact alignment happens, where you get the moon perfectly covering the sun and you get the shadow projecting on it. You can also see on this animation, one reason I like it on the one on the right is you can see why we do things to scale. Because if we do things not to scale, then you can actually see what's going on. You can see light rays or light paths and shadows, umbra and penumbra there. But if we zoom out and put it into scale, everything gets incredibly vanishingly small and hard to see. So when you see that not to scale written down, that's why. That's really why. But we're all gearing all this up for April 8th. April 8th, 2024, a little over a month from today, we are treated to this spectacular celestial phenomenon right here in the United States. And so I hope you're excited as I am. This is what we're looking at for the path of totality. So this stripe that's going from Mexico up through the heartland of the United States and then out through New England and Canada. This is the path of totality. So you have to be somewhere in this region right here to be able to see that solar corona. If you are anywhere else in the continental United States, you're going to see a partial solar eclipse. Very cool. It's worth going outside and observing, but not quite as cool as seeing the totality. I'm just not going to lie. That is really special to see totality. So why this path is so narrow is because of that geometric positioning that we were looking at before. The shadow of the moon casts a very small, about 100-mile wide path that sweeps along the planet. Down in the lower right, you can see what that path looks like zoomed out, so you can see the entire globe. It's in purple there, where the deeply shaded purple is where totality or the eclipse is near maximum, with totality that dashed line. And then as the purple fades out, that's less and less of a partial eclipse. So most of North America is going to be able to see at least a partial eclipse. Along the path, the eclipse comes on shore in Mazatlan, Mexico, sweeps up through in mid-afternoon through Dallas, through Indiana, through Ohio, Pennsylvania, Great Lakes, and then out through Maine and then Canada. The eclipse will last almost 4 minutes in these places, which is pretty spectacular because the one in 2017 just lasted a couple. So if you saw the one in 2017, come back. This is a fantastic encore, and important too, because the next total solar eclipse that's going to happen in the continental United States isn't for 20 years. If you want to see the next one in somewhere in the United States in general, 2033, the North Slope of Alaska is going to see a total solar eclipse. So we're still very long way from anywhere in the US from seeing a total solar eclipse. So this is another reason why it's very special on April 8th. All right. So what are you going to see during totality? This is a question I get quite a bit because it's a little bit misleading sometimes, the images that you see during totality. So the image on the right is a highly processed scientific image. The colors there represent different polarities of light, and then you can see this fine structure of the solar corona coming out of there. And that's usually the pictures that are published in papers and on, astronomy blogs, astronomy picture of the day. All of those great sources are going to show you that picture. It's gorgeous and actually scientifically very interesting, and we'll get into that in a little bit. However, what are you going to see with your eye? Well, it's a little bit closer to what you see there on the left. Still, that one doesn't really do it justice because it is quite spectacularly beautiful. That one looks neat, but not beautiful. The one that you can see with your eye is stunningly gorgeous. So when you do see a total solar eclipse, it's nice to think about what your expectations are for what you're going to see, because a lot of those eclipse pictures, especially even the ones from amateur astronomers, they use hundreds or thousands of images all stacked together to release all this intricate detail. And you don't often get a chance to see that with your own eye. So what else might you see if you're on the path of totality on April 8th and you have clear skies, which is another issue. April, not necessarily the best month for clear skies, but fingers crossed, we'll have clear skies everywhere. And what will you actually see? You can actually see some fantastically interesting parts of our closest star. First of all, you're going to be able to see a red ring around the edge. This is the middle atmosphere of the sun, called the chromosphere. It's called the chromosphere, chromo meaning color, because it's red. It looks red, and it has that appearance from the emissions, the elemental emission that's coming out of that layer of the sun. So the emission comes from hydrogen gas. We got a little lesson on that earlier, so you can actually see this emission with your own eye. This is one of the neat things. So not only can you see the outer atmosphere of the sun, you can see the middle atmosphere of the sun, the corona or the chromosphere, with your eye. That's what I did my PhD on, and I spent a long time looking at the chromosphere. must be more beautiful with your eye than with a telescope, I just have to say. But other things you're going to see during a total solar eclipse, the diamond ring effect and Baily's beads. These are really neat features. If you just stop and just give it a pause to think about, the diamond ring effect is this bright singular point of light, or Baily's beads are where, this bright ring that kind of breaks up into little bits, little twinkling bits of light. Those are caused by the rugged surface of the moon itself. So you have this sort of mountainous terrain, or maybe you have a crater on the surface of the moon, and then the sunlight peeks right through a valley right before it's eclipsed from our perspective. And that's sort of, I don't know, akin to maybe a sunset. You could think of that, of like the sun setting between the mountains and you just getting one last glimpse of the sun before it sets. Similar kind of thing, except with the moon. And except how we see it with this are these individual like little beads of light. Really neat to think about. Like the reason we see these things is because the Earth, because the moon isn't entirely smooth, and we can not only do that, but we can predict where these are going to be using the Lunar Reconnaissance Orbiter and all of the fantastic mapping it did of the lunar surface. So we have an amazing view of this topology. And the diamond ring effect and Baily's beads 100 years ago was this grand mystery of what was actually going on. Now we have a map down to predict exactly where you're going to see that and how. Prominences. That's the last part of the thing that I wanted to highlight here, which is these loops of material, this hot gas, this heated plasma that's lofted into the solar atmosphere by strong magnetic fields. You get these loop-like structures, or these like twisting loops structures coming out of the surface of the sun into the chromosphere. And you can see that with your eye. Likely because we're approaching solar maximum, you're going to see a lot of it. And so when you go into totality, you can not only see the chromosphere just smooth, the corona and its interesting structure, but also you're going to be able to see solar weather, or the origins of solar weather, the origins of space weather from those prominences and those loops. Maybe if we're lucky, we'll even be able to see an eruption, which would be even more amazing. You see all eruptions a lot of times sped up in animations. You might be able, over 4 minutes, might be able to actually see something erupt on the sun with your eye. So I am very excited for April 8th. All right, I would be remiss if I didn't spend some time talking about eye safety, because this is very important. Most of you probably know you're not supposed to look directly at the sun, but I've just been spending the last few minutes telling you you should look directly at the sun, so what gives? Okay. What you need is special eye protection for direct solar viewing. These could come in the form of Eclipse or solar glasses. The NASA has produced, I want to say, over 2 million glasses and distributed them around the country. I know other foundations and organizations have produced tens of millions of these things. So if you don't have solar eclipse glasses, check with your local library. They likely will have some, especially if they are, or your local astronomy club. Those are two great places that we've distributed lots of glasses to. If you don't have solar eclipse glasses, there are other options. You can find your friendly local astronomer. Likely they'll have some solar filters for either binoculars or for a solar telescope there. Those are two examples. If you do have some sort of magnifying device for the sun, a telescope, binoculars, a magnifying glass, anything, the solar filter has to be the first thing the sunlight hits. So it's sunlight, it hits the solar filter, and then whatever else is going on behind the scenes. I mean, it can be a camera, it can be whatever lens, but it has to hit that solar filter first. It could be a handheld filter like the one down in the right-hand corner, and you're wanting to look for the ISO standard, the 12312-2, the international standard for safe solar mylar. I just have to emphasize that we do not want anybody to get hurt. And if you're using a magnifying device, the risk of doing serious damage because damages go up. So if you're using some sort of telescope or binoculars, use safe viewing techniques, be very careful because we want everybody to do this safely. All right, so let's get back into a little bit more of the fun science. What do we learn from solar eclipses? Yeah, they're not just beautiful, but they're actually pretty cool things. So going back in history a little bit, we've learned a few different things. One of the cool things is we discovered helium using the sun. So back in 1860, don't remember the date, but 1860s, there was an expedition to take a spectra. This fantastic introduction because we took a spectra of an eclipse and we're trying to get an idea of what does the sun look like back in the 1860s? What does the solar atmosphere look like? And they were able to pick out the different elements and the different colors of light, and then they found a mystery color. And this mystery color corresponded to a new element, which was helium. And they named it after the sun, helium. And the helium on Earth is mostly found in the ground. We typically mine it. There's a little bit in the atmosphere, but where it was discovered was on the sun itself. Another major discovery, of course, which is the image there in the front, is the experimental proof of Einstein's theory of relativity. They were actually able to predict and then observe how much distant starlight was bent by the sun using a total solar eclipse. So they took images of the darkened sky of stars during the darkened sky of that during the eclipse. It got those plates, returned 6 months later to the same location on the Earth, took more photographic plates, compared the two, and they were able to see a noticeable shift from lights that were behind the sun, and the light was being gravitationally bent towards the Earth. Really cool stuff, and a really foundational principle for our modern society, and how we use modern technology was because of a lot of work Einstein did. Of course, there are Earth and Moon measurements that we continue to make measurements of. We refine measurements of Earth's and Moon's orbit, and we can also track the slowing of the Earth by the gravitational forces of the Moon using eclipses. We can track where the difference between an eclipse's predicted path and where the actual path is, and that difference between the predicted and actual path can give us an idea of how many milliseconds this Earth's rotation is slowing down by every year. It's something like one point something milliseconds per year that the Earth is slowing down by. It is not much, but it's not nothing either. So all of these things have gone into really a foundation for modern astronomy and modern solar physics. But there's also a little bit of an artistic side to this because before we had photographs, we used, scientists went out and drew pictures of the sun. And so we have a rich repository of solar eclipse paintings that date back even further. And the image on the left there is a painting from March 25th, 1857. That you can see solar structures that we know as helmet streamers and jets. We can actually estimate the size or where we were in the solar cycle based on these images, and even estimate the size of like the polar fields, the polar magnetic fields, based on the topology and the geography of what's going on in those drawings. If you go back even further, you can look at cave paintings. So here's a likely solar eclipse in Sweden. An eclipse happened there in 1229 BCE. The cave paintings date from about that period, and there's something that looks awfully like a solar eclipse. So these events have been really impactful for humans throughout history. The cool thing is when you can spot a conclusive drawing of a total solar eclipse in like in a rock art or some other early recording of eclipse history, you can pinpoint the location, which means that we can calculate more accurately where eclipses have been in the past, which means also we can calculate how much the Earth-Sun relationship has changed over the years. So these historic observations are still valid and valuable for modern day science. More recently, if we zoom all the way up to 2021, one of the really neat findings coming out of a decade's worth of solar eclipses, Shadia Hubble, a scientist at the University of Hawaii, has been looking at eclipses for probably longer than I've been alive. And she had made a really significant discovery using an 11-year cycle of eclipse observations. She discovered that the solar corona, this outer atmosphere of the sun, remains at a relatively constant temperature over a solar cycle. That's significant because the sun changes a lot during a solar cycle. It means that the mechanisms that burst out solar flares and erupts coronal mass ejections and have all of these dynamics on the sun aren't the process that's heating the corona. Because if they were heating the corona, then in solar maximum, you'd get a hotter corona, and solar minimum, you get a cooler corona. No. So something else is heating the corona. So it's really helping us solve one of those foundational mysteries in heliophysics, which is why is the corona so gosh darn hot? It is millions of degrees, and we don't quite know why. We have some good hints, but we're not quite sure. So using what scientists learn about the eclipses has really impacted the science that we understand now, as well as the science that brought us to today. It's fantastic. So in general, why do we care about eclipses in modern times? We have LRO that mapped the moon tremendously accurately. We have measurements down to the millisecond. Well, it's probably even smaller than probably down to the microsecond of how the Earth's gravity is being affected by the moon. We are getting fantastic measurements, but why are we still studying it? Well, there's the Earth-Sun relationship is one of those critical features that we don't really have a good handle on, and specifically how the Earth's atmosphere responds to the sun. And it's hard because the sun is on every day and off every night, and so this circular cycle of day-night cycle is what we have to estimate the effects of the sun on Earth's upper atmosphere. However, we have a natural experiment where we get to turn off the sun for just a few minutes, see what happens to the ionosphere, and then turn it back on. Why? Well, honestly, technology. We are a spacefaring species. We rely on space for everything. I don't think I can go to the grocery store without my GPS. And GPS signals are very affected by the Earth's ionosphere. This little diagram here that I'm showing you gives you a little perspective on what happens is that when you get these electron clouds, these electron irregularities, it can disrupt signals coming from GPS satellites to whatever receiver is on the ground. So being able to study the ionosphere during an eclipse where you can just flip off the sun and turn it back on for a bit gives us a really fantastic opportunity to take advantage of that and study the effects of Earth's ionosphere by the sun, or the effects of the sun on the Earth's ionosphere, and then how the Earth's ionosphere rebounds and changes and comes back again, what waves are propagated, how that energy passes down to other layers of the atmosphere. The other reason, of course, we are a spacefaring species at this point, and satellites, we have a lot of them. And Earth's outer atmosphere, the exosphere, puffs up when in solar maximum, when there's a lot of solar activity, there's more ultraviolet light that is absorbed by the upper atmosphere, the ionosphere and the exosphere, and it will actually expand. It'll heat up and expand. Well, that means that any satellites that happen to be up that far will just get a little bit more drag. They'll run into just a little bit more atmosphere. When satellites run into a little bit more atmosphere, that means their orbit changes just a little bit. And over time, that can change the lifetime and the characteristics of the satellite. So this is where a lot of, Department of Defense and the different military research branches are very interested because they have a lot of assets in space. NASA does too, of course, but we're both very curious about how the satellites change their orbit and how satellite drag changes based on effects from the sun. And we can do that a little bit more carefully, a little bit more accurately with this natural experiment. All right, so let's get to brass tacks here. Specific science investigations done during the 2024 solar eclipse funded by NASA. So there are 6 of them that I want to highlight. First, there's going to be some eclipse chasing, except not eclipse chasing with a car, but eclipse chasing with NASA's WB-57 high altitude research aircraft. So this is going to be flying at about 50,000 feet above Texas and chasing the eclipse. When you fly at that altitude, you get above the majority of the water vapor in the Earth's atmosphere, which means that any wavelength of light that's preferentially absorbed by water vapor is now visible to you. And so you can really do some interesting experiments. So This is this first experiment is a follow-on to something that was done in 2017. This is data that the team took, the Southwest Research Institute team took in 2017, and or calibrated to expose visible light structures as well as infrared light structures. So they're going to be targeting the infrared wavelengths and imaging at extremely high resolution and high cadence. So taking a lot of images in a short amount of time. In fact, one of their science targets is to look for asteroid belts that maybe are undetected right now. Maybe they're in the orbit of Mercury and haven't been seen yet. But using this infrared technique, they might be able to detect them as well. So it's a fun follow-on. They're going to get information to compare with 2017. 2017 was near solar minimum. Now we're near solar maximum, so there's interesting changes as well. So Shadia Habal's team out of the University of Hawaii is also flying on the WB-57 aircraft. They're flying spectrometers, and they're looking for chemical composition and specific outflows from the corona. So using spectrometers, you can actually measure changes in velocity of material, and so they're actually going to be able to track material as it leaves the chromosphere, it moves into the corona, and then further out. So that's also flying on WB-57 for the same reason as the other team. When you get above the clouds in the Earth's atmosphere, you can see a lot more interesting things. So hopefully they're going to have good weather no matter what, because they're so high up in the sky. That it'll be great. So that's another exciting WB-57, and you can see a nice little animation of the aircraft there. Next, there is a contest. I'm using that word lightly. It's a friendly contest for amateur radio astronomers. So this is the ham radio community, or ham-sci, led out of the this project is led out of the University of Scranton. And they're using an interesting property of ham radios. So ham radios are, consumer electronic radios. You can buy one yourself, and you can communicate with people over great distances by bouncing the radio waves off the underside of the ionosphere and then back down to Earth again. So when you have these bounced waves between 2 points, you have a really neat little neat experiment where you have point A on the surface and point B on the surface and some arc that connects the two. Well, one of those, it's kind of interesting. Maybe you can talk to somebody far away, thousands of miles away. But if you have hundreds of thousands of those, I think they're looking for 700,000 point-to-point contacts confirmed, you can build up a map like the one that you see here on the left. And this map is a reconstruction of the observations that were done between transmitter and points, transmitter and receiver, and the 2017 eclipse. Using this technique, they're looking to go even further this time by reconstructing the underside of the ionosphere, because those waves bounce off the underside of the ionosphere. Depending on those fluctuations, those gravity waves that are set up, the other undulations that happen in the ionosphere, those pathways will change and you'll get different ringing effects. And so they can use sophisticated models of the ionosphere to actually reconstruct the underside of the ionosphere and its changes during a total solar eclipse. So this is research led, but it relies on a large community of ham radio operators. If you yourself are a ham radio operator or know of somebody who is, I would highly encourage you to join this project. They're always looking to recruit more people, and it's incredibly valuable. This science will really go a long way to discover the dynamics of how the ionosphere is changing during an eclipse. Another team that's targeting the ionosphere is the Super Darn network. So this is a auroral radio network. There are radars set up across the world. They're going to use these radar networks again to study the ionosphere and specifically looking at a little bit more of how the ionosphere transfers its energy through the atmosphere. So the ionosphere reacts to the solar eclipse, but then it relaxes after the sun comes back, relaxes in a sort of a physicsy word of relaxes, as in it returns to its normal state again, with a lot of sunlight. But all of those changes somehow propagate and yeah, propagate out from that effect. And Super Darn is looking to track those changes and understand how they change. Number five that I wanted to highlight was a radio telescope. So most people think of radio telescopes as looking at deep space objects, and you had the like large Arecibo disk or large Arecibo antenna that was going deep out, observing the deep cosmos, or some sort of large interferometry array. This one is using a single disk antenna to observe the sun. You're like, wait a minute, you're observing the sun in radio. Yeah, the sun emits all wavelengths of light. So typically the Golden Valley, what is it? Goldstone Apple Valley radio telescope observes the sun in this sort of pattern where it zigzags across the sun, taking measurements, and you build up an image sort of like the one on the upper right-hand side. Interesting. I mean, you get some changes. You can see some hot spots of where solar magnetic activity is. Fairly low resolution, though. If you change your reception wavelength, so you're looking at 8.4 gigahertz, you can distinguish a little bit more, but you are really pushing the limits of the natural physics of radio waves, as in they're big, and it's hard to see small things with big radio waves. If you use an interferometry, you can actually derive that EOVSA image there, and you can see a lot of different artifacts through there. And then for reference in the lower right-hand side is the sunspot magnetogram, where you can actually see the ground truth, the actual magnetic fields that are measured on the sun using a space-based system. Okay, so what this team is doing, really a fun idea, is they're using this moon's disk as a natural occulting disk to watch it slowly cover up an active region, one of these magnetic hotspots on the sun. And as the solar disk slowly covers up, they can just sit and take measurements over that spot over and over again and get an ultra high resolution image of what that spot looks like. So they're not going to just see a solar active region like the ones that are on these examples here, where it's just sort of a bright blob. They're going to get extremely high resolution images of what an active region looks like in radio wavelengths. It's a really fun idea to use the natural geometry of the moon, and they're going to get some amazing science out of this. I hope I can come back to you in like a year and tell you all about the fun findings. Last but not least, NASA is doing a sounding rocket campaign as well. This is where we launch a suborbital rocket. It's launching out of Wallops Island. It's going to go up to about, I forget the maximum height. It's about 100 miles, I believe, and fly up into the ionosphere and take measurements as it's on its trip up and on its way back. So they're actually going to launch 3 rockets. This is a follow-up campaign to the annular Eclipse campaign launched out of White Sands, New Mexico. Similar campaign, 3 rockets before, during, and after the eclipse. And then they're going to do the same thing in Wallops Island. Again, probing the ionosphere, but this time they're actually flying through it. They're actually going up into it and out of it. So they can measure densities. They can measure magnetic fields. They can measure the ionospheric or the ionization state of the ionosphere, and see how that changes based on the total solar eclipse. So all of this is part of a bigger effort by NASA called the Heliophysics Big Year. So I wanted to just spend a last few minutes talking about the Heliophysics Big Year. This is an initiative that NASA has put together to really bring everybody across the nation into heliophysics for a moment. So many of you might not know the word heliophysics. Maybe it even sounds sort of intimidating, heliophysics. But the big year is an opportunity for everyone who has an interest in the sun and the sun-earth relationship to get involved. It started back in October 14th with the annular solar eclipse. This is where we saw this moon pass in front of the sun, and we had this ring of fire effect around the outside back in October. Of course, the main event, April 8th, 2024, the total solar eclipse. And then this big year, in all the meanings of the big year, as in it's more than a year and it's also just full of a lot of cool stuff, is wrapping up with the closest approach to the sun by Parker Solar Probe. So Parker Solar Probe is NASA's heliophysics flagship mission. This mission is flying closer to the sun than humanity has ever flown before. That is dipping into that outer, or that I would guess the inner layer of the corona. It's past the Alphane surface, so it's where the sun can actually still have an effect on the coronal processes. It's passing through that surface December 24th of this year. So what this year represents is an opportunity for you to participate in some of these events, see it at an eclipse, pay attention to Parker Solar Probe's perihelion, but also to think a little bit about how the sun affects your life. There are monthly themes, and NASA social media is pushing out those themes. But what I really would challenge you to do is just take a minute to think about the sun's relationship on your life and how you think about the sun. The sun is our closest star, but we often think of it as weather. And so this year really gives you a bit of time to think about how the sun affects your life and understand those processes. So thank you very much for your time, for your attention, and I will stop sharing and pass it over to my colleague.
All right. Thank you, Michael. That's wonderful. John, if you would like to join us, and John Maple is 10 years here at the Space Telescope Science Institute, and I've had the pleasure of working with him for all of those years. In particular, he is an educator, a former elementary school teacher. We bring in teachers who have experience in classrooms to come help us design our materials here in the Office of Public Outreach. And John and I had some wonderful times going around giving educational talks, mainly to teachers, actually, teaching teachers how to teach the students. John, let's see, the thing I was going to tell you about John, I always have to use humanizing, is known about John ever since I met him is he's a big, huge Orioles fan. The Baltimore Orioles have not been the best team over the past decade, but he's made it through the lean times, and we now have a competitive baseball team here in Baltimore, so that has made his life a lot better this year. So, John, take it away and tell him what you're going to say. Tell him about the eclipse.
Thank you so much, Frank. Appreciate that. And it is the good times are coming for us in Baltimore because everyone's attitude and life
John, we're
revolves.
seeing your presenter screen, not the.
Thank you, Frank. Let me stop this. Here. There we go. Thank you, Frank. So what I'm going to talk about today is that here at the Space Telescope Science Institute, we are the Science Operations Center for Hubble. We are the Science and Flight Operations for Webb, and coming soon, the Nancy Grace Roman Space Telescope. And the thing about space telescopes is they're great looking out into space, but in a special event like a solar eclipse, Hubble, Webb, and Roman will miss out on those. Not that they're going to miss out on the science, but they just can't turn themselves around and take a look at the sun. We have very sensitive instruments that don't like looking at the sun. They love looking at other stars, just not our sun. So what I'm going to talk about is what those special instruments are that our space telescopes have that can work with and help us make discoveries around other stars. Specifically also thinking about exoplanets and gravitational lensing. So the special instruments that we're talking about are coronagraphs, and they're instruments that can block out the light from other stars so that we can see those dimmer objects around them. Exoplanets we look at and we can tell they're there because a planet goes in front of the star. We can measure that sunlight and we know that it dips, so there's got to be something there. We can analyze the light that passes through that planet and look at and see, oh, what are those cool things that are in that light? What's getting blocked? What's coming through? That tells us through spectroscopy what we're looking at and what that planet is. And the big question is, like, is there life out there? Is there life on this planet? Could this planet have life? And then I think one of the coolest things about Hubble, when I started about 10 years ago, it was starting to be a big thing, was gravitational lensing and how we can see farther because there's massive objects in the way and it bends light. It's just mind-bending science and ideas that when I came to start working at Space Telescope, I was like, I am now not anywhere close to being a smart person working here because the people that work here are just on a completely different level. So that's kind of a highlight overview of the things we're going to talk about here. First of all, my favorite is Hubble, workhorse of astrophysics, can do everything and anything. And so Hubble has that one of the special tools called a chronograph. It's on the instrument on Hubble called the Space Telescope Imaging Spectrograph, or STIS. So Hubble's able to look at things in space that are very bright, block the bright part out, and take a look at what cool things are nearby and take spectra. And that spectra is really how astronomers and scientists can look at an object and say, this thing has methane on it, this thing has water vapor on it. Because obviously Hubble does not fly to the nearest planet, star, galaxy and go, hey, what's going on here? We can only take in what is sent to us, and that's the magic of Hubble and Webb and soon to be Roman. So just like Hubble has coronagraphs, Webb also has coronagraphs. So we look at inside of Webb, we have NIRSpec, NIRIS, NIRCam, and MIRI. This very fancy image that is created here at the Space Telescope Science Institute by our amazing graphic designers, have this little icon for coronagraphs. So the NIRCam, MIRI, and NIRIS all are able to block out that extra bright light. So Webb can take those exacting details and spectra that other telescopes, maybe ground-based, other wavelengths aren't able to get. And that's what gives us the amazing insights that Webb is sharing with us now. And then the soon-to-be really cool one coming out is Roman. Roman is a different kind of telescope because Roman will take an image of a survey of a much larger area than Webb or Hubble would do, but still be able to get that Hubble quality image. So on Roman, there's going to be a chronograph instrument. It's a technology demonstration. So they're sending it to help inform the next space telescopes to understand how is this going to work. It's the first of its kind to go into space to try and help us detect these extremely faint exoplanets. So Roman will take a massive image and then it'll be a lot of working in surveys and in the I'm blanking on the word now, but looking back at those observations of lots of people looking at the same image to find these exoplanets that maybe are possible with this instrument. And so this is an image of Beta Pectoris from Webb recently. This is one that's showing how the coronagraph actually works so that everybody understands stars are not a five-pointed star shape. They're just something us teachers, we love to put on papers, make everybody think this is what a star looks like. In this case, this star is not really there. We put it there so that you're like, this is where the star is. And this kind of a Saturn-y kind of looking shape with a circle in the middle here and the elongated triangles coming off the side, that's actually the coronagraph that's blocking out the light. so that we were able to see cool things like the cattail coming off the right side of the image. And we're not quite certain what that is, and that's the wonderful thing about science, is that we find one thing and we'll find 10 other questions to go along with it. So look forward to more Webb observations to find out what else is going on here. So this is one example of a coronagraph observation. This is another one. Once again, more teacher stars. We have one here, 4 here at the bottom. These are 4 different images, 2 by NIRCam, 2 by MIRI, in different wavelengths of light, looking at this exoplanet, HIP 65426b. It just rolls off the tongue. It's an exciting name to say. It's the next one all the kids are going to be into. But it's very cool because Webb is able to get this detailed observation of this planet, because our coronagraph can block out the light, and we see these individual images. These 4 images here are not 4 different planets. They're all 4 the same planet. So coronagraphs, very powerful to help us find more things in space that you can't see. Now, as I said before, that with the eclipse, we look for other eclipses. Those are exoplanet transits, where we see one body pass in front of another so that we can measure that light. Kind of like in this diagram here. A lot going on here. We'll talk through it here. So we have this big light gray ball. Let's say that's our star that we're looking at, and orbiting around it is the planet. And we can see in this kind of circular graph beneath that is the amount of light that we can observe as the planet's orbiting around the star. So we can measure this bump that goes down and back up. And that amount of light that we can see is what astronomers look for when they're going, we have an exoplanet. Let's find out what's going on here. So there are multiple ways to find an exoplanet, but according to, this is from NASA's Exoplanet Exploration, 4,156 planets have been found through this transit observation way of discovering exoplanets. The next closest one is 3,000 away. So transit, exoplanet transit observations are the best and most productive way that we have found exoplanets looking through the stars. Now, if you want to go yourself and go, I want to see what are these planets, NASA has a great applications called Eyes on Exoplanets. You can explore all of these worlds. In this application, you can find exoplanets discovered by individual missions. You can find by individual, get back here, individual ways to find those exoplanets. So it's after tonight, if you're like, I want to find out more about these exoplanets, here's a place that you can go find out about individual exoplanets. Right up here, this is a picture of the application. I didn't want to run it because it would crash my computer. But up here, this bright yellow box, I have browse destinations. It'll take you to different exoplanets you're looking for. So you can find those interesting ones. You can find those ones found by transits, those that are maybe found other ways, found by Hubble, found by Webb. Lots of fun ways. It's another fun application just to, take yourself and put yourself in the role of a scientist and find out what's out there and kind of dig into space on your own. That brings us to gravitational lensing, which is, it's beautiful and it's awe-inspiring. This is just a little diagram to kind of get a grasp of what the topic, of how it works. On the far left, we have a galaxy, and that light from the galaxy is coming through a cluster of other galaxies, and that's about the middle of the image here. And you can see the light's coming in one direction, but when it hits that group of galaxies, it's bent, and it's bent towards us, so that light, the more light's coming to us, and that image we can see clear, we can see what's behind this group, because these galaxies have acted like a lens focusing that light towards us. And we get the awesome pictures like this. This is a Hubble image on the left and a Webb image on the right of the same place. So this is one of the awesome things about Hubble and Webb being telescopes in space at the same time, is that we can take images of the same place in space, look at it with Hubble's powerful UV and optical, and compare it with Webb's infrared, and together make great discoveries about what's out there, what is beyond what we can see, either in wavelength or actually through the use of gravitational lensing, pulling things so we can see them that wouldn't be possible just with a telescope by itself. And this is a galaxy cluster, so we're seeing stars, we're seeing galaxies. The actual lensing is these strips and ribbons that are kind of going through the image. But we also don't lens just galaxies. We also lens black holes. And one of the powerful things about Hubble is that we can see things over time and see that change as this black hole is changing its environment around it. And so that's one of the things we can use with lensing. And then this is of the star Arendelle, that the farthest star we'll be able to see, and it is also a product of lensing. So Hubble was able to observe this because of looking through the gravitational lensing of the cluster in front of it. Now, I myself am not a scientist, so I bring these pretty pictures instead and say this is of the a molten galaxy, where the galaxy itself has actually been lensed and looks like it's melting in space. I think it's a really cool image. This is one you can find on Hubble site. We have a zoomable image of this, so you can zoom in and see all the cool little details now of what's going on in this galaxy, in this cluster. But like Frank also said, I'm an educator, so what I bring really is I bring resources and things so that you're excited about tonight. I want to go farther. What else can I do? So there are two places that I suggest to look for more information about eclipses. The first is science.nasa.gov/eclipses. It's a great website. NASA's pulling together all of its resources there, helping you find places where eclipse events are happening. But also at Space Telescope, we are a part of the program called NASA's Universe of Learning, and we've put together a web page on our website, universallearning.org/eclipse, where we go through in more detail gravitational lensing and exoplanet transits. On that page, we share more videos, more content. If you want to see pictures of gravitational lensing, we have a website called astropix.org, along with webtelescope.org and Hubble site. We also have interactives on viewspace.org. All these resources are available on our website, along with other exoplanet activities, images, and articles for you to read. That is where I am for tonight. Thank you for your time. Let me
All right. Well, thank you, John.
Thank you, Frank.
Giving a good places for people to explore more, because that's one of the major things we like to do with all of our outreach programs, is not just give you information, but also give you pathways to explore more, both through NASA and through the universe of learning. Thank you both for your presentations on it. I have a couple, well, now into the question and answer section. So I have a couple questions. When people talk about, well, first of all, to demonstrate Michael's adherence to say, look, you got to have good solar eclipse glasses. I went and grabbed my solar eclipse glasses from 2017, and I absolutely cannot see anything. I've got a bright light shining in my face. These are solar eclipse glasses, and it says right here, safe for solar viewing. Okay, please make sure that you get yours, especially if you're not in the path of totality. Because if you're not in the path of totality, you need the eclipse glasses to be able to. Once you get totality, then you can take the glasses off, okay? But only while it's total. Once the totality finishes, then you got to put them back on, right, Michael?
Absolutely, yeah. Thanks for clarifying that. Also, if you're in the path of totality and you don't take your eclipse glasses off, you're going to miss the best part. So remember to take them off. I mean, you're not going to see anything in the eclipse glasses during totality. So you also, I just want to impress that, you naturally have instincts not to look at the sun. You, I don't know, come out of a shadow and into the bright sun and you squint, you look away. So you follow those instincts. If you are looking into the sun and it's uncomfortable, if you have your eclipse glasses on and it feels uncomfortable, go with those instincts. It'll help keep you safe. Also, if you have eclipse glasses from 2017, give them a little inspection first. Just, take a look at them, make sure there aren't any damage or pinholes or major scratches. If there are damage, I would encourage you to cut them up and get new glasses. But if they look like they're in good shape, the solar mylar is robust enough that it should be fine. You should be able to use them again this time.
Yeah, even a pinhole can be damaging when you're talking about the brightness of the sun. All right, so we've had a bunch of questions go through. We've had a wonderful chat on YouTube. Grant has been following the YouTube chat and recording interesting questions. So Grant, why don't you join us and tell us what you found on the YouTube chat?
Absolutely. And our first question leads right into what you were talking about. If you wanted to have a good viewing experience, what would you suggest other than specially designed solar glasses in order to do a proper observation?
So yeah, there's a few different options for observing an eclipse. One, of course, is the eclipse glasses, right? Another great way is using indirect methods. Most people, at least I remember growing up and seeing a partial eclipse, and you have a cereal box or a box you stick on your head, and you put a pinhole in the side. There's actually instructions on eclipse or science.nasa.gov/eclipses. Yeah, thanks, John, for mentioning that. So if you want to build a box like that, you can. Ultimately, pinhole projection is actually a really fun way of observing a partial eclipse. So if you're going into totality or you are not going to experience totality, get a piece of cardboard or just a sheet of paper, some sort of heavy stock paper, and make a design of pinholes with it. Just punch a bunch of holes, and then you can move it above the ground, and you can make a design yourself, and you'll see all these little crescent shapes. So you're creating a camera for yourself, a camera obscura, the original camera, to observe the eclipse. And so you can see all these crescent patterns. Also, go out and observe a tree in the bright light, and you'll see all little crescent shapes. You can see some really beautiful things. In addition, take a look around at the world around you, especially as you're going to totality. Animals will start behaving differently. There are all sorts of anecdotal accounts of animals doing weird things. So keep your eyes out for that. You don't know. And just also take a look at your neighbors and the people around you that are observing this eclipse. People, especially in totality, it's an emotional event, and people have an emotional reaction to it. It's worth taking a moment and appreciating that, because you're there at a very special moment in the grand scheme of the cosmos, one single place and one single time, in order to witness this. So I would say a holistic viewing is the best way of doing it. Looking at the around you, looking at the light itself. If you have eclipse glasses or some sort of ways to do it, look directly at the sun, do a direct solar viewing. If it's clouded out entirely, tune into nasa.gov. We'll have a live stream going the entire time, and we'll have live telescope feeds, and we'll still be able to bring you all that great eclipse footage.
Yeah, that last comment about it's clouded out. This is April. There's going to be a lot of clouds, especially up in the Northeast. If you really, if there were, I've got a friend who's going to Cleveland for the eclipse, and I was like, you're going to have a 50-50 chance of whether or not you're going to see the eclipse or not. And so, if you can get down southwest into Mexico and into Texas and such, you have a much higher chance of seeing it. But there was one other piece of advice that always struck me. If you're going to see your first total solar eclipse, just watch it. Okay. Don't try to take photographs and observations because the few minutes pass so quickly. Really enjoy it. And then you learn all the things that you'll need to know to really totally prepare. I've got some friends who are eclipse watchers and eclipse chasers, and they have all three of their separate of their cameras all set up to take different types of photograph, and they've got these giant checklists that they're going through to make sure that they get their observations. That's really difficult when it's your first one.
Yeah, you're going to see beautiful images online. You're going to have probably people that you're next to that have seen eclipses before take amazing photographs. So if it's your first one, just have a really good time.
So speaking of preparations, John, was there any particular resource that you might recommend for people to really understand the idea of an eclipse in terms of the resources that somebody might look at before they go, so they really understand what they're looking at when they get there?
I was about to ask that.
Oh, thank you, Grant. Sorry, I didn't mean to step on you.
If I was going to prepare to go and see the eclipse, I would start with NASA's website, that nasa.gov/eclipses. They really have pulled together a lot. Their heliophysics experts like Michael are working to make all those materials available, and are first-rate materials to understand what's going on.
Do they have an eclipse duration calculator on there? Because, you don't have to be exactly on the center line and you still get a really good, really good view
Yeah,
of it.
so there should be a duration calculator coming out. I was just in a meeting today where they got the iframe embedded on the website, so it should be out soon. If you saw the one from the 2023 annular eclipse, it will have a very similar feel to it. In addition, there are several NASA partners that are putting out eclipse duration. So if you go to the National Solar Observatory, this is a NSF funded project. They have an interactive Google Eclipse map where you can put a pin anywhere and get the timings of an eclipse and the totality. So yeah, the National Solar Observatory is a fantastic resource for that too.
Fantastic, because it's important for people to know how long you find the place you want to be and how long the eclipse is going to be. But also, if you can't get there, how much of a partial eclipse are you going to get? We're going to get what, 80% here in Baltimore or something like that, or 85?
I think it was around that.
Yeah, that's
It was larger than I expected because we're well off the eclipse line.
Yeah. So I want to have a follow-up and then I want to talk about the eclipse line. John, since this is your area of expertise, what sort of like citizen science or like in the chat, one of our returning viewers is asking a local library if they have a telescope lending program or like an event or something like that. Is there anything that you would suggest based on your experience?
Not necessarily for the eclipse and for borrowing a telescope, but if you're interested in participating in a citizen science experience with exoplanets, Universal Learning has two programs. One is DIY Planet Search. You can find that on our website, and Exoplanet Watch. I would start, if you're brand new at it, start with DIY Planet Search. It's a much smaller, easier entry into the program, and then Exoplanet Watch is for that little more into it, experienced amateur astronomer taking data and sharing it with the whole community.
Thank you. I always like to highlight that because I don't think the majority of people who interact with the content know that they can be a part and make like help do what we all do and get to talk about. Okay, so that will lead us into the next one, which is, are there going to be any cascade effects from this? Like, is the eclipse going to cause interruptions or disruptions for other types of observations, um, other science going on at the time?
In general, no. The eclipse is an anticipated enough event that if an observatory that is going to be along the path is going to make observations, takes advantage of the eclipse and make observations related to the eclipse. There's going to be planets visible, for example. There's a chance if you have a correct setup, you could observe Mercury too. It'll be right outside the limb of the sun, so it's going to be a fun time. I think you can see every planet that is observable with the naked eye during the eclipse. I think they're all above the horizon. So if you're in totality, there's a chance to see all of them. Of course,
That's
caveat.
so cool.
Yeah, it would be amazing. You have to get a place without trees and clouds and like lots of things gonna get in the way. But if you are an enthusiast along that route for nighttime observing, look up their star charts because you're gonna see some really cool stuff.
From the light pollution.
Oh yeah, oh yeah. But in general, other things, we do know that eclipses cause scintillation in the atmosphere. So there are pockets of electrons and charged material up in the ionosphere. So if you rely on GPS for any sort of fine alignment, it can cause disruptions there. So I mean, if you're using an amateur telescope with GPS aligned, probably not an issue because it locks onto a signal and it's just going to sit there. If you're trying to land, like, I don't know, a jet on an aircraft carrier, yeah, you might want to take that into account. So, to varying degrees, there might be some disruptions, but in general, it should be pretty minor and pretty fleeting.
I mean, I think that one of the bigger impacts on science is that, you're going to study the ionosphere and how it reacts, and how it changes. And that helps us predict how all those satellites in low Earth orbit, which by the way includes the Hubble Space Telescope, what kind of atmospheric drag we'll be able to predict better the atmospheric drag. Hubble is safe as far as we know for another decade or two. But this understanding that we gain during these eclipses will help us refine those numbers.
Awesome. Yeah, that's what I was trying to think. Like, there's a cascade effect from all of this that affects everything going on. And the chat said 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn are going to be visible, at least for us in the northeastern
Yeah, we've
section.
had a very active chat today, guys.
Yeah, shout out to the chat, by the way. Y'all are great. So that I'm reading through to grab another one. Frank, if you have one offhand, go ahead.
Let's see. John mentioned NASA eyes, and I would just you mentioned eyes on exoplanets, but they have NASA eyes on the solar system, and they have a ton of this NASA eyes. I just would recommend that as a general resource for if you go to eyes.nasa.gov, I believe it is.
Yeah, you're correct, Frank.
Because that's a great resource for many different topics and such. Okay.
Absolutely.
The other thing that I wanted to give Michael a chance to complain about something. You talked about solar prominences, right? And one of the things that always bothers me is that so many people, especially those who think they're doing documentary tile stuff, call those solar flares. And it's not a solar flare. I just wonder what does a heliophysicist say to things like that?
An eye roll, and then we say, well, actually, so yeah, I mean, solar activity is all it's all driven by magnetic activity. So it's easy to get it confused in terms of which one is what part. The solar flare is when you get a magnetic reconnection event where a tremendous amount of light energy is released. So this is electromagnetic spectrum energy. It bursts out in a bright burst of light. You can observe it in ultraviolet. You can, if they're big enough, you can even observe it in white light, that's a really big one. But the solar flare produces a lot of that light energy. Then what can go along with it is a big disruption and reorganization of magnetic fields. And when that happens, they can actually move material off the sun in a coronal mass ejection. And so what ends up happening is that they get conflated because they can happen at the same time. You get a flare, it disrupts things, and then a mass ejection happens. They can also happen separately. You can get a flare without a mass ejection and a mass ejection without a flare. So that's why they're different. And those filaments are these big plumes of matter that are just hoisted up into the atmosphere and held there by quasi-stable magnetic fields. It doesn't take a whole lot to make that quasi-stable unstable, and then you can get a mass ejection. And so that's how you get all of these terms sort of swirling around in your head, because it is all contributing to space weather at the end of the day. It is all sweeping out through the solar system. It all impacts planetary atmospheres, Earth's atmospheres, astronauts. And so this is sort of part of the ecosystem that we exist in. But as scientists, we break it down into like phenomenological effects.
All right, Grant, you have any more questions
Yep.
out
Yeah.
there?
So this is this might take a second to get through. So JWST is obviously too far out. It's at L2. It's not any way involved with this, and I would imagine that Hubble, it's too close to be a realistic observation for Hubble to do anything related to this because it's essentially like right next to it in galactic terms. But that's what the chat is talking about now, is what would be able to do something like an observation for this if any of the low or outer Earth orbit or any stations that are up now, because we can do things with ground-based telescopes, ground-based observations, but we're having a debate right now to see if anything out there right now could observe this, but I think it's too close if I'm not mistaken.
Yeah, it's pretty hard to observe it from a space-based platform. Space is big.
There's
A lot of room out there. It's
our
hard to
quote of the
things.
evening.
You're right.
Lecture series. Space is big.
Yeah, I think you can quote me on that. Yeah, Michael Kirk says space is big. Yeah. Or you
I'll
can just
use that.
NASA scientist. NASA scientist says space is big. End of story. Anyway, so so it's hard to get assets positioned in the right place. Even getting something that's maneuverable like the International Space Station in the right place at the right time, it's hard. It's challenging to get those orbits adjusted, and it takes a lot of time of preparation. The one sort of, I don't know, maybe it's a bit of a cop out, but it's worth mentioning, is the Discover satellite that's sitting out at L1. It's between the Earth Sun, the first Lagrange point, and it's looking back at the Earth, and you get a full view of the Earth, and you can see the shadow of the moon going across the Earth's surface. And sometimes you can even see the moon transiting in between the satellite and the Earth. Look it up online. There's some really cool images. They don't look real. That's how cool they are. They look like they're simulated, but they're actually real images of an eclipse happening. So
that movie of the dark spot moving across the Earth, I use it every time I give an eclipse talk.
Yeah,
That's so cool.
Beyond that, in terms of solar viewing telescopes, they're just not in the right place. They don't have the right geometry to be able to take advantage of it. So the ground is really your best bet.
All right.
Valid.
I have a interesting question, because you mentioned that Earth is slowing down 1.8 milliseconds every year, or something like that.
I think it's every decade. I think I
every
said year,
decade,
but I
whatever.
think I misspoke. But yeah.
But that's all right. But the point is that Earth and the moon are slowly getting further and further apart. So one of the questions I never bothered to answer for myself, but I've got a heliophysicist to answer it for me. How many millions of years before we will no longer be able to see a total solar eclipse? The moon will be too far away, and we'll only get the at best annular eclipses.
Yeah, that's a great question. And in fact, we're a little bit past that golden era. We're getting more annular eclipses than total eclipses, just by a couple percent, but we're past that peak. It'll be another 500 million years. So yeah, we got some time. But that it's slowly changing. You're right. And so as the moon drifts further away, that perfect alignment gets less and less, which means that to see a total solar eclipse now, the moon has to be closer than average in its orbit in order to see it. So yeah, it is changing, and eventually it will only be annular eclipses, and eventually we'll just get a transit. If you go look up the transit on Mars, some of the Martian rovers, you see a Phobos or Deimos transit across the sun, and that's eventually what it'll look like here on Earth. Again, we have 500 million years, give or take. These calculations get pretty difficult once you start trying to extrapolate out for millions of years. But
Yeah.
yeah, about 500 million years. Yeah, factor of 2 in there.
Yeah, I gotta say that shot of Phobos going in front of the sun from Mars is just one of the great science shots ever. All right, we're getting towards 9:30. Grant, do you
Sure.
have it in?
I
One more
got
question or
two
two
quick
more? Okay,
ones,
two more
depending
questions.
on
Let's go.
if you know what the first one is. Let's see. Fort Worth Astronomical Society. Welcome.
Shameless
But
plug.
also, yeah, talk about the Soundscape project. I don't know what that means, but you might know what that means.
Yeah, so NASA Soundscapes is a fantastic citizen science project. So that is run by the ERISA Lab. They solicited a whole team of volunteers to get these specialized equipment, these listening devices, to actually record nature sounds before, during, and after an eclipse to get an idea of how nature is reacting to an eclipse. So insects, birds, animals, that sort of thing. They no longer have the time in order to ship them out anymore. So now they're recruiting observer listeners. So you can go to eclipsesoundscapes.org and sign up to be an observer and run an observing campaign. Take notes for yourself. You can help out teams that do have these listening devices and really participate and contribute. So that's one of those citizen science campaigns that is, as much as you want to participate, you can do it in sort of a minor way, or you can get incredibly involved, help with data analysis, and really get plugged in. And so that's a really fun one. The other one to check out is Sunsketcher, sunsketcher.org. This is a University of Western Kentucky. They are trying to determine if there are gravitational anomalies in the sun, like, I don't know, dark matter in the sun, other gravitational anomalies, other flow patterns we're not seeing. And so what they're doing is recruiting as many people as they can to take images using their smartphone of the total solar eclipse. They're going to aggregate these hopefully hundreds of thousands of images together and get an incredibly accurate view of what the eclipse is, compare that to simulations, and see if there are any slight differences. Again, one or two images not going to help out, but if you get that power of statistics, you can really beat down the noise and actually start making some really cool measurements. So sunsketcher.org is another one to check out.
All right. Okay, last question, Grant.
Unless John has anything to add with that, I think that's a perfect place to end.
Okay. We got lots of opportunities for you to go out and observe the eclipse with your eclipse glasses. Okay, just making sure we say that yet again. You can never say that too often, right, Mike?
I think I have to go, if I don't say eclipse at least once an hour, I think I don't get paid or something.
There we
I
go.
think that's how
Okay.
it works these days. Yeah.
And so please get out there and even if you're not on the path to totality, get some eclipse glasses, observe the partial eclipse, read about it, understand, and as Michael said, try and understand our relationship with the sun here on Earth and how it affects us here. Go to those websites that John gave you and try and learn what you can and see how it's not, we have eclipses on exoplanets. That's how we discover exoplanets with eclipses. We create artificial eclipses in our telescopes in order to see planets around other stars. You know, there's this science of eclipses extends everywhere. All right. Okay, next month, I just remind you, on April 2nd, gamma ray bursts, spectacular explosions from the distant past. We'll see you then. Thank you for watching.